Hello everyone, my name is Lucas Pons from Metra in Spain. I'm responsible of Work Package 4 product Resc in CROSSBOW project. In this webinar, I will show you some of the main features of the product and give you some insights on the architecture of the product and how it fits within the CROSSBOW infrastructure. The European Commission endorsed a set of milestones with regards to clean and safe energy generation in the region. These goals push the regions to invest and promote the installation of renewable sources of energy in order to adopt a more sustainable energy mix. This increasing RES penetration affects the system operator core activities and must be carefully handled to avoid grid security problems. Even though all countries in Europe are advancing in this direction, there are a lot of differences between them in terms of RES deployment, services provided, integration type, etc. Typically, RES management is organized through coordination centers for renewables. The aim of such centers, sometimes known as dispatching centers, is to aggregate the tasks related to the management of renewables in a system for reducing the complexity of the task associated to connecting these units to the grid. Within CROSSBOW, Resc plays the role of a coordination center for renewable, and its main role is to assist in the integration and operation of renewable power sources. The Resc functionalities are offered as services to the RES plants. This relieves the plant managers from having to implement the processes by themselves and will also give them access to new added value services that will imply new sources of income and new exploitation opportunities for their resources. In countries in the region with low presence and penetration of renewables, these centers may not be strictly necessary, and their features could be directly assumed by the system operator. But this is a model that does not scale well, as the number of RES units increase and require an increasing integration effort for system operators. Also, even though the energy mix of the countries change very slowly due to the cost of new investments and also linked with other political barriers, it is reasonable to assume that this will change sooner than later, mainly due to the following. First, the worldwide trends in energy production technologies are clearly pointing at cleaner energies that are increasing their efficiency and profitability, and the EU 2020 goals enforce EU countries to boost the adoption of the RES technologies. The Resc adoption in the region will not only help countries with big RES portfolios enhancing their internal RES management processes, but also will help other countries choosing the best and most appropriate model to develop and exploit their portfolio. This is the architecture of Resc. The product is composed of different components, depicted here inside the green boxes. In the center box, there are a component pieces of software that compose the core of Resc. These components are meant to be installed at the premises of the RES operator and mainly deal with the tasks of data gathering and storage from RES assets, control command dispatching, market participation optimization, and KPI calculation. The green box at the left comprises a Resc component for curtailment optimization based on power flows, real-time and forecasted information. This requires having access to the power flows, and that is why this process, even though it is developed under the Work Package 4 umbrella, provides services to the system operator, and thus has to be installed at the TSO infrastructure. The results of this process are transmitted to the core Resc that will implement the optimal curtailment calculated and approved by the system operator. The green box at the bottom represents the components and gateways required to be installed at the RES plant. It deals mainly with the task of communicating with the local plant SCADA, translation of the information to the appropriate data model, submission of data to the core Resc, and reception of curtailment commands. Besides the communication among the internal components, Resc communicates with some external components, like dispatching centers in the region, that are used to get information about RES plants in the countries with no need of deploying additional gateways at the RES plants. Also communicates with energy markets and with weather forecast providers that will allow to obtain and generate the generation forecast for the different plants in the region. These are the main functionalities offered by Resc: monitoring of the plants, command dispatching, advanced curtailment management services, RES generation forecasting, and energy market participation. We will go through these tasks in the next slides. The first task is the portfolio monitoring. Resc includes a web application for RES operators that features several visualization options for the RES portfolio, including dashboards, maps, hierarchical views, and detailed views of the different assets. So this is the RES web application. At the main page, there is a dashboard with the main information of the portfolio, including current energy generation and forecast, generation distribution by country, daily evolution of the real and forecasted energy generation, number of plants connected, and information about the active curtailments, and some market indicators, including the energy sold in each market, with prices and obtained revenues. The portfolio view presents the list of plants in a hierarchical view that can be filtered out and sorted. For each plant, the current active and reactive power is presented, as well as the forecasted generation and the curtailment set point, if any. By clicking in a plant, a slider is shown with details. More details can be accessed by clicking on the name of the plant. This page presents the main data of the plant, including real-time measurements and static information of the plant and the location of the plant. The historical evolution of the metrics can be seen in the specific tab. The historical evolution of the metrics can be seen in the specific tab. The second main task of Resc is the command dispatching. Resc is able to submit commands to the RES plants without bothering the RES operators with the specific details of the protocol used by the plant. The command may come from two different sources. The RES operator can specify a control command manually from the Resc web application, and the TSO operator can specify a control command manually from the WAMAS web application, which is the CROSSBOW graphical user interface for TSOs and regional security center. This command will flow to Resc and will be submitted to the appropriate plant. So we can show this in the user interface. For instance, this plant is currently generating 4 megawatt hour, and we can establish a set point here of 2 megawatts. We can also specify the reason for that and the duration in minutes. So by establishing the set point, the limitation now is active, and after some seconds the plant will start sending the new active power according to this limitation. The section set points show information about the currently active power limitations, like the one we have just established. Also, the other mechanism for sending the manual curtailment is by using the WAMAS user interface. This is the WAMAS user interface. In the section network, the current status of the grid can be seen, including the substations and power flows between them. Here, only the main substations, mainly 400 kVs, are shown, and the color depends on the country where the substation is located. By clicking on a substation, the elements of the substation are shown in a slider. And from there, the generators can be selected in the appropriate voltage level. For instance, this is one of the generators that are connected to this substation. The set point of the generator can be established from here, including the curtailment amount, the reason, and the duration. The curtailment eventually will be received by Resc and activated by the RES plant. So there are two sources of generation set points, one in the Resc user interface and another one in WAMAS, which also connects to Resc. Also, Resc provides two mechanisms for facilitating the curtailment management. The first one is the curtailment distribution. Resc allows TSOs to define generation limits or curtailments for areas, being these areas sections of the grid where a need for curtailment has been identified. These areas can be defined by substations, geographical areas, islands, etc. And more than one RES plant can be included in each of these areas. Upon reception of area curtailments from TSO, Resc must distribute the curtailment to specific RES plants. Different algorithms have been tested in Resc for such a distribution, and in any case, TSO operation of the grid is easier by leaving the details to the RES dispatching center. Curtailment commands are distributed according to equality and fairness criteria, and normally the curtailment impact is alleviated for the portfolio, or at least equally distributed. We can see a demonstration of this by going to the WAMAS tool. Then selecting a given substation. In this case, a CONSCO substation has a number of generators linked, connected to different voltage levels. If the system operator needs to reduce the power injected through this substation but does not want to bother about establishing set points for all the individual generators, the limitation can be established by substation. Eventually, this limitation is received by Resc. So we can establish the limitation for the whole substation. And eventually, this limitation will be received by Resc and will distribute the limitation according to different algorithms. We can see how these limitations have been distributed and different curtailments have been established for the different elements linked to this CONSCO substation. Besides the manual configuration of control commands for RES plants, Resc provides a component for the TSO that calculates the optimal set of remedial actions, curtailment commands. WAMAS tool for system operator and regional security center is periodically analyzing the power flows of the region from the common grid model files, and in case of congestions or non-N-1 contingent situation, the Resc remedial action optimizer is invoked. The optimization makes use of the power transfer distribution factors (PTDF) analysis, along with the ancillary services prices taken from the ancillary services market. Then the TSO can simulate the effects of the remedial actions suggested by the optimizer before accepting and distributing them to the RES plants. We can see how it works by using the WAMAS tool again. In the section network, we can select a given instant in the future to obtain the forecast of the power flows according to the CGM files generated by the Regional Security Center. So we select one of these forecasts. It takes some time before loading. After some seconds, we obtain the power flows of the different lines connecting the substations in the region. We can select a given line that we consider can be problematic or has a forecasted congestion and access the details on how the different generators contribute to the power flowing through this line. The list presented here contains the generators with its contribution factor and the actual amount of energy generated that is effectively flowing through the line. These factors are obtained by making a sensitivity analysis of the CGM files. The list is sorted by its contribution factor, thus presenting at the upper part the generators that have more influence in the line power flow. Here we can select an amount of energy flowing to reduce, and the system calculates the minimal curtailment that are needed in order to obtain such reduction. For instance, here we can tell WAMAS to reduce in 30 megawatts the power flowing through this line. So by clicking here, by clicking here, the curtailment amounts are shown in the list, and the summary is presented at the top. The curtailment can be accepted, and then if we agree with this curtailment proposed, which is total curtailment of this generator, total curtailment of this second generation, and partial curtailment of this third generator, we can apply these actions. And WAMAS allows to simulate the effect of the control commands by clicking on the simulation button. Here we have some actions to simulate, and then we can start the simulation. Here we have 70 megawatts, and we have generated actions for reducing this power flowing through this in 40 megawatts. So if we click on simulate, simulation is started. After some seconds, the effect of the actions in the power flows are presented. As we wanted, the power flows reduced from 72 to 32, which was the objective. If the simulation provides the expected results, the control commands suggested can be accepted by the operator, and then they will be scheduled to be executed at the appropriate time, just like the manual control commands. Another functionality of Resc is the production of Resonation forecasting. Production forecasts are periodically generated for most of the RES assets in the region. Predictive models have been built for the assets and fed with weather forecast data. Forecasts are used mainly for market participation. And this market participation is another of the features of Resc. Resc is able to participate in different energy markets, in this case the intraday and the MFRR Ancillary Services market. For the intraday market, the first thing to remark is that the market used is the CROSSBOW Ancillary market that is connected through a REST API interface. The algorithm bids the energy in an aggregated way. The assets are clustered based on the production cost, which normally depends on the generation type. Total amount of energy to sell is obtained for each cluster and time period. Then, the most beneficial energy buy orders in the intraday market for the close time horizon are accepted according to the cluster characteristics. The remaining energy is offered in the intraday market at different prices. If no buyers are found, the prices are lowered until the production cost is reached. This position closing mechanism is used in case of forecasting error detected that may produce imbalances. The software is configurable in terms of time horizon, acceptable degree of risk, granularity of the offers, etc. The obtained revenues for the energy in the portfolio are distributed, and the price schema is based on historical prices taken from ENSOE. The other market integrated in the MFRR Ancillary Services market. Again, the market interface is the CROSSBOW Ancillary market product. Resc supports MFRR market participation for upward and downward regulation. MFRR offers are sent automatically for the next hour, up to 30 minutes before delivery. Downward regulation bids includes the total amount of energy potentially curtailed. Upward regulation bids include the total amount of energy that the plants can increase. Normally, this amount is close to zero, because RES plants used to trade the whole amount of forecasted generation in the day ahead and intraday markets. But Resc market participation algorithm features a bidding module where a configurable amount of potential generation is not traded in intraday market and left for being offered as upward regulation energy in MFRR market afterwards. TSO service activations are taken from MFRR market close to the real time. KPIs are generated to assess the effectiveness of the market participation strategy, and dashboards are presented with the information. In Resonation interface, these KPIs can be seen in the market section. We can select KPIs for different countries. In the upper part, KPIs of energy produced and economical revenues are presented for the last hour, as well as for the current day so far. The share of benefits obtained in each market is presented in a pie chart, including intraday and MFRR market participation. Average prices are also presented, and at the bottom, different time series are presented, including actual and forecasted generation, energy prices evolution, and revenues obtained in the different hours of the day.